Hi class, we are now on chapter 8.2b. We're going to deal with calorimetry. Calorimetry, so scientists and engineers often need to measure how much heat is transferred from one source to another. Experiments that measure heat flow are called calorimetry experiments. The two most common calorimetry techniques are coffee cup calorimetry and bomb calorimetry. One is constant pressure, one is constant volume. In this lesson, we'll look at these two techniques and how we use them to gather information about heat transfer. So when I mean constant volume is the volume of the solution doesn't change, where in the other one, the pressure doesn't change. So a coffee cup calorimetry is exactly what it sounds like. In this method, water is placed in an insulated cup, which is a styrofoam cup. That's what you would do if you were in person in lab, is use styrofoam cups for this, and there would be two, so it would improve the insulation of the cup, and which is covered with a cork and a thermometer. The system to be studied is placed inside the coffee cup, and the reaction or change is allowed to take place. Because styrofoam is a very good insulator, nearly all of the heat involved in the change is absorbed or released by the water. By measuring the temperature change for the water, we can determine the amount of heat that is gained or lost by the system. For example, if we wanted to measure the specific heat of a block of iron, we would heat the block and then place it in a calorimeter. When the hot iron is placed in the cool water or room temperature water, heat is transferred from the iron, which is hot, to the room temperature water. According to the law of conservation of energy, the total energy inside the coffee cup is conserved. This means that the metal loses the same amount of heat that the water gains. That is, the negative, here, the negative Q, that means heat's leaving it, and you don't see it, but there's a plus here, which means that the heat's being transferred to the water. It's the same numerical value. In this equation, the minus sign shows the metal is losing energy. In previous lessons, we saw the heat gained or lost by material can be described by the equation Q equals ms delta T, change in temperature, where m is mass, s is specific heat, and delta T is the change in temperature. By combining these two equations, we can say that the mass of the water, the specific heat of the water, the change in the temperature of water is equal to the negative, which heat leaving, the mass of the metal, the specific heat of the metal, and the change in temperature of the metal. So as long as you have, there's 6 variables, as long as you have 5 of them, you'd be able to solve for the other one. To find the specific heat of the metal, we would rearrange the equation, which is what you do here. Rearrange the equation as shown here. Let's look at the example type of problem. And there's a negative sign to account for the negative of the metal, the heat lost. Okay, so this looks like a lot, so I'm going to break down the steps because it's not as difficult as it appears to be. A chemist heats a 26-gram sample of an unknown metal to 100 degrees Celsius, then places it in a coffee cup calorimeter containing 52.1 grams of water at an initial temperature of 20 degrees Celsius, so approximately room temperature. At some time, both the metal and the water reach an equal temperature of 24 degrees Celsius. What is specific heat of the metal? So in order to solve this problem, we first must recognize that the heat gained by the water is equal to the heat lost by the metal. That is, the Q equals negative Q for the metal, Q water. Based on this, we can use this equation to show before, which states the specific heat of the metal is equal to the negative the mass of the water times the specific heat of the water. Basically, we're looking at this one, and we isolated the specific heat of the metal, which is what we're trying to figure out. We might suspect this is a metal of a certain substance. So let's say I'm just going to randomly throw something out there, but let's say that we suspect this metal is iron. One of the ways that we can determine, or process of elimination if it is iron, is by doing an experiment and checking the specific heat value for that metal. If it matches iron, then this is one more way that we can say, yes, this is iron, and then go on to other tests, or no, this isn't iron, and we can figure out, based on that value, what metal is close to that numeric value for the specific heat. Okay, so basically, let's tabulate the data we know before we attempt to solve this. So this is where you get the mass of water, the mass of the metal, the change in temperature for the metal, Now this is where it's a little confusing. The final temperature for both the water and the metal is 24 degrees Celsius, but the metal started at 100 degrees Celsius. So let me explain why. The metal gets placed in a big clear test tube. And if you were in class, you would have had one of these. What you do is it's similar to sticking this test tube, but a dry test tube. Inside the metal is just the metal. There's no water inside the metal with the metal. You stick that test tube into a boiling pot or a bowl. In your case, it would have been a boiling beaker, boiling water. But the metal stays dry on the inside of the test tube. So the water is surrounding the test tube and the heat's being transferred into the test tube where the metal is. When the metal reaches about approximately 100 degrees Celsius, which is when water boils, what you're supposed to do is you take the temperature when you see the highest temperature reached of boiling is when you transfer the metal into and you do it very quickly. You take it from the test tube, take the test tube out of the boiling water and transfer it into the coffee cup with the room temperature water. And then you start taking temperature of the water. And eventually you'll see that here it was 20 degrees, but it stopped at 24 degrees. So that 4-degree difference is heat that got transferred from the metal to the water. So hopefully that makes sense about the initial and the final. So the initial is 100. The final is 24 degrees. That gives us negative 76 degrees, which we need. We need this because specific heat values are not negative. So we need a negative and a negative. What will cancel out, a negative and negative equals positive, and will leave us with a positive value, which is what we need. Now the water, the final was 24, but the room temperature initial was 20. So that's the 4 degrees. So you plug everything in, and if you did this right, this is specific heat, which means you have 3 units. And if you cancel everything out and leave the rest, then this is what you should have at the end. Okay, so let's look here. The specific heat of water is 4.184, the mass of the water. So I've gone through most of that. Now we're ready to insert the values. So that's all you're doing is you're inserting all the values for everything. And we can cancel the units, giving us a final answer of 0.44 joules per gram degrees Celsius. Let's look at a second example involving coffee cup calorimetry. Aluminum chloride has an unusual property. It absorbs heat when it dissolves in water. This compound is used in instant cold packs because it takes heat from its surroundings. We can write this endothermic reaction like this. So you see the heat plus ammonium chloride produces, and this is solid, produces ammonium chloride in aqueous solution. So I lost my place, sorry. How much does this temperature drop when we dissolve ammonium chloride in water? Of course, this depends on how much we use, how much water we use as well. But we can measure the amount of heat absorbed by doing a coffee cup calorimetry experiment. We fill a coffee cup with a known amount of water, and then we add the ammonium chloride, measure the change in temperature. The heat lost from the water is equal to the amount of heat gained by the solid. That is, Q solid is equal to Q aqueous. Since we know that Q equals mass times specific heat times change in temperature, the equation becomes Q solid equals mass of the aqueous solution, specific heat of the aqueous solution, and a delta T of the change in temperature of the aqueous solution. So, for example, a 10.4 gram sample of ammonium chloride was combined with 100 grams of water in a coffee cup calorimeter, causing the water temperature to decrease by 6.20 degrees Celsius. Based on this, how much heat energy was required to dissolve the sample of ammonium chloride? Calculate the heat solution for ammonium chloride in kilojoules per mole. In this example, ammonium chloride absorbs heat energy as it dissolves. The amount of heat absorbed by the solid is equal to the amount of heat lost from the aqueous solution. We can solve this using the relationship Q solid equals the mass times specific heat times change in temperature of the aqueous solution. The mass of the resulting solution, here's the mass, right? The mass of the resulting solution, I'm losing my place again. Sorry, the mass of the resulting solution includes both the water and the dissolved ammonium chloride. So we write M aqueous as 110.4 degrees, zero point 0.4 grams. Because it is mostly water, the solution has a specific heat nearly identical to that of water. So what they're saying is because it's water, we're gonna treat this as water. The change in temperature of this aqueous solution is minus 6.20 degrees Celsius. The next thing is that we need to determine the mass, the moles of ammonium chloride. So we take the moles of ammonium chloride, which is the 10.4, and we use the molar mass, and it leaves us some moles. But here, let me jump up. I think I'm jumping ahead. So we take the mass here, the specific heat, and the change in temperature, and that gives us 2.86 kilojoules. That is the heat of change, the heat energy from the solid. So now we need a heat of solution involving the ammonium chloride. So we need the moles, which is what's taken from actual ammonium chloride, the sample, not counting the water, and then we plug everything in. So the heat of solution is the energy, so this is Q over moles. And this gives us 14.7 kilojoules per mole. So this is, again, the heat of solution. Okay, bomb calorimetry is not what it sounds like. This technique measures the heats of reaction for fuels and other high energy chemical changes. In bomb calorimetry, a test sample is placed within a heavy steel container. Outside this container is a second container which is filled with water and equipped with a thermometer. A pair of ignition wires detonates the sample. The gases produced cannot expand, so all the energy is released as heat into the calorimeter. Remember when I said one's constant volume and one's constant pressure? This is obviously constant volume because the pressure increases. That's why it's called bomb calorimetry, where the coffee cup is constant pressure because even though it's got a top on it, it's still open to the atmospheric pressure. So the pressure on this one doesn't change. Okay, so a pair of ignition wires detonates the sample. The gases produced cannot expand, so all the energy is released as heat in the calorimeter. Using a heat capacity, which is joules over degrees Celsius, for the calorimeter, the amount of energy produced in the reaction can be determined. For example, we can use a bomb calorimeter to determine how well ethanol can work as a fuel. To test this, we will place a smaller sample of ethanol and excess oxygen inside the bomb calorimeter. We would then ignite the sample inside the container and measure how much the temperature of the calorimeter increased. The following example illustrates this idea. A chemist places 20-gram sample of ethanol inside a bomb calorimeter with a known heat capacity of 28.72 kilojoules per degree Celsius. When ethanol ignites, the temperature of the calorimeter rises from 22.04 degrees Celsius to 42.74 degrees Celsius. How much heat did the ethanol release? Calculate the energy released in kilojoules per gram of ethanol. So it's telling you what the units are. So this is Q over the mass. Okay, so let's take a look at this. From the initial and final temperatures, we see the temperature changed by 20.70 degrees Celsius. The heat capacity of the calorimeter, so this is where the heat capacity, we get that, and we solve for C. Okay, what I mean to say is here's the equation that we're going to use. Using this relationship, we determined the heat released for this reaction. And what we can see here is we set it up. Here is our heat capacity. So this is what's given to us. That's C. That's what you see here. And then we have our temperature. The degrees cancel out, leaving us kilojoules, which is exactly what we want. And it's 594.5 kilojoules. So now we're going to take this answer, plug it in here because this is asking for the energy released in kilojoules per gram of ethanol. And we're going to take the mass of ethanol and place that on the bottom. This gives us an answer of 29.7 kilojoules per gram. Okay, so here is a coffee cup calorimeter, measures heat changes at constant pressure, and bomb calorimeter measures energy content, heats of reaction in food and fuels. So if you ever want to know how much calories are in food, this is how they determine it. They determine it by pretty much doing a combustion reaction and determining how much energy is given off. All right, so let's take a look at some problems. A chemical reaction takes place in an aqueous solution inside a coffee cup calorimeter. The mass of the solution is 110 grams. If the solution temperature increases by 5 degrees, how much heat has the solution absorbed? So heat is what it's being asked. So what they're saying is they're considering the solution equal to water, since it's mostly water, and we're going to use the specific heat of water. And here is the equation that we need. And pretty much all we do is we plug everything in. So we take the mass, we have 110 grams, we're using the specific heat of water, and then we're going to take the change in temperature, which they've actually given us the change and not the initial and final temperature. And then it gives us, this is from my calculator, but based on the fact that we have two sig figs, the answer is 2,300 joules. A 10-gram piece of metal is heated to 100 degrees Celsius, then placed directly in a coffee cup calorimeter containing 75 grams of water at 18 degrees Celsius. At some time, the water warms to 20.28 degrees Celsius. What is the identity of metal? So let me explain this one. This sounds really complicated, and it's not. Separate what you know from the metal, separate what you know from the water. And just remember, the final temperature will be the same for the water and the metal. So in this case, what you have is you have for the metal, you have 10 grams, and this is the initial for the metal, and then the final temperature for the metal is this. So you have three things you need from the metal. We don't know the metal, that's what we're trying to figure out. Now let's take a look at the water. You have 75 grams of water in a coffee cup at 18 degrees Celsius. That's what it started with before the experiment. And it ends at 20.28 degrees Celsius. And that's about right, because water doesn't, no matter how much it's heated, remember, it has a very high specific heat. So it can take a lot of heat and the temperature will only raise a few degrees. So let's see what it is. Now, I do mine a little different than what they showed you here. Not here. Here. Not there. Here. They have you plug everything in all at once. I don't do that. I do it in steps. So I'm going to show you how I do it. Neither way is wrong. Neither way is right. It's how you feel comfortable doing it. But I'm going to show you. So this, I always figure out the water first. I figure out Q for the water. So this is how I do it. I take the mass of the water, the specific heat of the water, and the change in temperature of the water. I am getting the Q, because the Q, once I determine this, I will now know what the heat from the metal was that was transferred. So I plug everything in, and it gives me 715.464 joules. Because I'm doing this in steps, I'm not rounding. I'm leaving everything intact until the very end. So I'm going to take this amount, and now I'm trying to figure out the specific heat. So once I determine Q of the water, there's a negative sign. Remember, we have a negative sign. I am now going to plug that in. So I'm going to take this and plug it in here where you see. I'm going to take the 10 grams of the metal, and then I'm going to take the initial and the final. This negative sign is going to cancel out this negative sign, and it's going to give me a value. So I do it in two steps. I do the Q of the water, take that Q of the water, plug it in to the Q of the metal for the specific heat, and then solve for the specific heat. I like doing that better than plugging it all in one thing like that. It just, it's easier probably to do it all in one shot. But I felt when I learned it as a student, I broke it down into two steps, and that's just how I know how to do it now. I wouldn't even be comfortable doing it the other way. So from there, the negative signs will cancel out because specific heat values do not have negative values. And then I can look it up here. So I can see that aluminum would have 0.897. I have the 3 units I need to, and that is going to be A for the correct answer. A chemist conducts a calorimetry experiment on an unknown metal. The mass of the sample is 52.4 grams. The chemist heats the metal to 100 degrees Celsius and places it in a coffee cup calorimeter containing 95.4 grams of water. The temperature of the water rises from 21.9 to 23.2 degrees Celsius. What is the heat change for the water? What is the heat change for the metal? And what is the specific heat of the metal? So this looks like it's a complicated question, but really all it's asking you to do is solve it, just like this one. You're just going to take everything and solve it. Because the heat of the specific heat, well, the heat change for the water ends up being the heat change for the metal. So once you plug this in, then you get this one, and then you plug that in, and then you get the specific heat. So it's exactly like the problem previous. So here it is again. I did the water, plugged it in, had the amount, did not round it, plug it in. Here's a negative sign. Take the mass of the unknown metal, take the change in temperature of the unknown metal, and then it gives me, because we're dealing with 4 sig figs here, should be 4 sig figs. This one looks suspect. If I was going off this, I would say 3 sig figs, but this is the answer they gave. I'm going to say it's 3 sig figs. Yeah, see, I did it as 3 sig figs. So this should actually be rounded to 1 more sig fig because of the 3 sig figs. So this should be 0.130. Wait, no, 1, 2, 3. Actually, I take it back. My apologies. 0.129 joules per gram per Celsius. So it will be 0.129, 3 sig figs. So let's take a look. What is the heat change for the water? So I rounded it to 3 sig figs for this final answer. I rounded this one to 3 sig figs for the final answer. And then I was able, oh, look at, I did it right here. I did it with the 3 sig figs. So this was not rounded. This is rounded. A bomb calorimeter like the one shown has a heat capacity of 13.12 kilojoules degrees Celsius. When a sample of charcoal is incinerated, inside this vessel, it releases 33.58 kilojoules of heat. By how much does that temperature of the calorimeter change? So we want to know the temperature. So here we go, we use, here is the standard formula. We change it to what we need, which is temperature in this case, and then we plug everything in. So Q is 33.58 kilojoules, and then we have the heat capacity, which we have here, and these cancel out, leaving degrees Celsius. So the answer is 2.559 degrees Celsius. A 40-gram sample of fuel mix is placed in a bomb calorimeter with a heat capacity of 450 joules per degree Celsius. When the sample is ignited, the calorimeter temperature rises by 2.4 degrees Celsius. How much heat was released in this reaction? So it's asking for Q. So we're going to leave Q alone. We're going to plug in C, which is the heat capacity, and we're going to plug in the temperature. The degrees Celsius will cancel out, and the answer will be 1080. However, this is 2 sig figs, so it's going to be 1100 joules. A 2-gram sample of a glazed donut was placed in a bomb calorimeter with a heat capacity of 3.54 kilocalories per degree Celsius. The sample was completely burned, causing the temperature of the calorimeter to rise by 2.02 degrees Celsius. How many kilocalories of energy were stored in the donut? So we're going to then take the Q. We want to know the Q, which is kilocalories. So in this case, we take the 3.54 kilocalories per degree Celsius, times that by the temperature change, which is 2.02, and the answer is 7.150 kilocalories. 3 sig figs, 7.